So my name is Christina Andrade. I am a research professional at the University of Minnesota. I also am a core team member of Grandma, which is the parent collaboration to Kilonova Catcher. So we have the Professional Telescope Network and we have our Citizen Science Network. So Grandma, or the Grand Rapid Advanced Network dedicated to multi-messenger astronomy, is a professional network, and they produce Kilonova Catcher. So that's amateur astronomers and astronomers of any kind can join and facilitate our research. And so Kilonova Catcher is a citizen science project dedicated to the discovery of the optical counterparts to gravitational waves and other fast transients. So we are a community of amateur astronomers. We have 189 registered users across all continents, 159 individual telescopes, and 14 remote telescopes that you can purchase time on. We perform live follow-up observations of the optical counterparts to gravitational waves and other fast transients. So our members collaborate with scientists and contribute to the field of multi-messenger astronomy. And it is a very hand-to-hand relationship between the scientists and the astronomers within Kilonova Catcher, as the core team members are the same. So what is multi-messenger astronomy? You'll see me use this term a lot, and those who have spoken to me before will also hear me use this term. And so multi-messenger astronomy is a field of science. And so I want you to think of how astronomers detect things at a distance. And so you would see the Hubble telescope. That's electromagnetic radiation. That's light. It observes with light. You have gravitational wave detectors, which are long lasers with mirrors, and there's a whole mechanism, and I'll explain that later. You have neutrino detection, and you have cosmic rays. Which of these would you consider telescopes or observatories? Absolutely, Hubble is a telescope. But are these, the rest of them, observatories? So how do we, as astronomers, detect things at a distance? And we can compare it to how humans detect things at a distance. And so we have eyes, which are designed to detect light. We have our ears, which are designed to detect a different type of wave, sound. And so sound waves require a medium to travel along. It's energy, it's a flow along air, for example. And that's how we hear sound. And we have smell, which is designed to detect particles. Now, astronomers don't taste anything to verify stuff. We leave that to geologists. And so notice that these detectors look absolutely nothing like each other. And so now we can go back to what multi-messenger astronomy is and how astronomers detect things at a distance. And we have now our eyes to the universe, Hubble, the JWST, the Nancy Grace Roman telescope that's soon to launch. We have our ears to the universe, which are gravitational waves. We, like sound, gravitational waves flow across the universe. And then we have our nose to the universe, which is neutrino detection and cosmic rays. And these are different types of observatories, but they're not all telescopes. And so now we get to the meat of this presentation, kilonova and gravitational waves, our eyes and ears to the universe. And I'm sorry if my water bottle offends anybody. It's a Mets one. So what are gravitational waves? So gravitational waves are the event that occurs when two super dense objects merge. And so this collision releases such power that it perturbs the entire universe itself. According to Einstein, gravitational waves consist of an oscillatory space warp, an oscillating stretch and squeeze of space. How do we detect that? How do we detect that our entire environment, the universe itself, is oscillating? So these observatories, called interferometers, use mirrors spaced several kilometers apart to detect tiny vibrations from passing gravitational waves, or oscillations in the diameter of the universe. They are capable of detecting a change of less than 1/10,000th the charge diameter of a proton. And we have several different interferometers or detectors. We have two in the United States, LIGO 1 and 2. One is in the upper Northwest, and one is in Louisiana. We have Virgo in Western Europe, and another Virgo detector to be built in India, and then we have Kagra in Japan. And so here is an example of how gravitational waves are detected at these observatories.
To measure the stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
So when thinking about gravitational waves, a question you can ask yourself is, to what extent does one event interact with the rest of the universe? That is what gravitational waves are. So how do gravitational waves interact with the universe? And so I've made this abstract claim in my last slide, but how does it really function? So gravitational waves travel at the speed of light. That is the limit of travel, speed of travel in the universe. We all know this. So when compared to how light travels, gravitational waves travel at the same speed. However, they are not the same thing as light. They do not carry photons. However, when we look at how it propagates, so how do gravitational waves propagate? So you're seeing here in the figure is the progenitor, or what causes gravitational waves, which I haven't gotten to yet, merging together. So these two spinning objects collide. And so gravitational waves propagate in all directions, kind of like throwing a rock into a pond. However, strength and polarization depend on the viewing angle. So the way we feel or detect these waves depends on where we are. If you're standing directly in line where the, let's say, two black holes collided, you might experience a stronger or different kind of stretch and squeeze effect than if you're standing at a different angle. So either above it or directly at it, you'll experience something different. This is because gravitational waves have polarization, which means they shake space in different ways depending on how they were created. Because sometimes the two bodies that merge come out together like this, or they come together vertically, depending on what the event is like. And so how do gravitational waves interact with mass and gravity? So just like light, gravitational waves can be lensed around massive objects, just like light bending around a galaxy. So light interacts with EM fields, while gravitational waves only interact with gravity itself. So this means gravitational waves pass through objects like galaxies or dust clouds without getting scattered or absorbed. Unlike light, light will get scattered and absorbed. All right. But gravitational waves don't function like that. So when passing a very massive object like a black hole or a galaxy cluster, both light and gravitational waves will bend, but gravitational waves will persist in a pure form as it propagates. It will not be scattered like light is. And so how do gravitational waves disperse over time? So light has the inverse square law. So gravitational waves do not function the same way. So 1 over r squared is how gravity and how light slowly diminishes over time. Gravitational waves only do it as a function of their distance, so they propagate and maintain their energy much, much slowly and for much longer periods of time. So how can we observe gravitational waves? How do scientists know from a non-optical messenger if there is an optical source of this event, of this gravitational wave? So Kilonova Catcher are not gravitational wave interferometers. They're not gravitational wave detectors. We are a group of telescope users, a group of astronomers. And so what causes gravitational waves are Kilonova Catcher. And so Kilonova are not to be mistaken for supernova. Kilonova are powerful transient astronomical events. And by transient, I mean that it evolves over time. So a transient is an object in the sky that dims over a period of time. Kilonova are short transients, a few hours to a few days, when compared to supernova can last for weeks to months. And so kilonova occur in compact binary systems when two neutron stars, two black holes, or a combination of the two, called a neutron star black hole merger, combine, or when they collide. And so kilonova generate gravitational waves with unique waveform evolution and higher peak frequencies. So BNS mergers, which is what we primarily want to look for, our primary focus, our scientific focus is to look for binary neutron star gravitational wave alerts. And so how do we know that? How do we get information from gravitational waves? Because we're just getting this non-optical source, this non-optical alert. That's what first comes to us. That's what we first get. All right, we're scientists, we're sitting at our desk and our phones go off. LIGO, Virgo, and Kagra have sent an alert out. They detected a gravitational wave. It says neutron star black hole like it did on February 6th. But how? How do we know this? Well, waves, the gravitational waves carry information about their progenitors or about their source. So the mass, the spin, the distance of the objects that collided in their wave properties. So they have this information in their wave properties, the amplitude, the frequency, the wave evolution.
Right, the frequencies having a wave processes.
Yes. And so the kilonova are, like I said, binary neutron star mergers, binary black hole mergers, or neutron star black hole mergers. So there's three different kinds. And
High
so
frequency, long duration chirp.
Richard, do you have a question or a comment? You're either that or your mic's open.
So these three progenitors, these three different types of kilonovae will produce different gravitational wave evolutions. So binary neutron stars have high frequency gravitational waves, a few kilohertz, whereas a binary black hole merger will have, low frequency gravitational alerts between 10 and 100 hertz. And so then the binary neutron star mergers will have a long duration chirp lasting up to a minute. And what is a chirp? So in the context of gravitational wave detectors or detections, all right, a chirp is a characteristic of the wave evolution. It is when there is a sudden increase in frequency and amplitude for a particular duration. This is how we're able to classify gravitational waves as ready for KNC to observe them, if they are observable by KNC, because we're not going to observe two binary black holes. There might not be anything to observe. But binary neutron stars are bright. Those have an optical counterpart, right, of a gravitational wave. And so when compared to neutron star black holes, which is going to be like a mixed bag of characteristics. So binary neutron stars are going to have a weaker amplitude because there's lower total mass, because neutron stars, while compact, are relatively small. And black holes are going to have, a lot more mass, so they're going to have a stronger amplitude. And then neutron star black holes are a mixed bag of characteristics. And so they're a little bit more interesting to analyze as a gravitational wave scientist, but as an astronomer, you're really looking for that binary neutron star detection. And so why do kilonova generate gravitational waves? And I feel like this is something important to go over. Black holes and neutron stars are super dense objects. A neutron star is the collapsed core of a massive supergiant star. So supergiant stars are 10 to 25 solar masses, or 10 to 25 times larger than our sun. When a neutron star forms when a massive supergiant runs out of fuel and collapses due to its own gravity. So it leaves this high density core behind. So what happens is basically that the nucleosynthesis, the nuclear fusion going on inside the star, is not exerting enough outward pressure, enough outward energy to compensate for the size of the star that is the current star. And so what happens is that it collapses in on itself. And all these atoms join and create neutrons, just an abundance of neutrons. And then we just have a star made out of pure neutrons. And so neutron stars are the smallest and densest currently known class of stellar objects. And black holes are also super dense objects. And so these super dense objects colliding and spinning at each other just absolutely warps the universe and creates gravitational waves. And so what is so significant about Kilonova Catcher? Why do we want to study kilonova? Well, understanding how matter behaves in superdense environments is incredibly important to our overall understanding of quantum physics and general relativity and how gravity functions at various scales. It also helps with black hole science. Kilonova produced the heavy elements we find in our universe. So gold and platinum, all the heavy elements on the periodic table come from Kilonova, and a process called the R process, and of how different molecules are able to be excited, or these elements, these atomic elements are excited and then joined together to create heavy elements. That's a whole other scientific process, and name dropping technical theory here, but yeah, it's called the R process, and it produces gold, platinum, all these exciting things. They're faint and fast fading. They are rare cosmic events. So it's difficult to get, one neutron star, but then two together orbiting. And this means it had to survive not only the length of the original star's life, but then be in the right environment to create a neutron star and then another one. And so they're rare. Another reason why we want to study, so that last point, they're rare. To kind of like build on that is that there's only been one detection where we have been able to get a very clear binary neutron star gravitational wave alert, observe the binary neutron star, the kilonova, observe the merger in a full photometric, full light spectrum, all right? And we were able to prove that they're associated with short gamma ray bursts. This has never been done before, and it's never been done afterwards. And so on August 17th, 2017, LIGO and Virgo, there was an alert that went out. And it was the first time that a gravitational wave was detected by was confirmed by non-gravitational means, which means it was the first neutron star collision detected. So the aftermath of this merger was seen by 70 observatories on 7 continents and in space across the entire electromagnetic spectrum. It was a significant breakthrough for multi-messenger astronomy. Now, you guys might be thinking, oh, this girl is off her rocker. In 2015, they proved gravitational wave alerts for 2 black holes. For 2 black holes in 2015, we were able to prove gravitational waves existed. But it wasn't until afterwards they were able to prove that they could be produced by binary neutron stars when we could observe them. So not only could we get a confirmation that, hey, gravitational wave alerts exist, but we could also say, hey, we know exactly where they're coming from. We know exactly what the flags are for these events. And that's what makes, GW 170817 so significant. And it's what makes Kilonova Catcher to be in such a unique position, is that we are doing live follow-up, which means there's an alert, grandma receives it, and we say, hey, astronomers in KNC, can you guys observe? And so you guys, as astronomers, will be doing observation science with us. You would be understanding the data you're receiving alongside the scientists. And so the paper for this detection was, I think there was 17 pages worth of authors. I don't even want to go talk about the acknowledgement section. It was absolutely super long, just a phenomenal paper, both in how many people worked on it and in what it proved. It totally jump-started a new division of science called multi-messenger astronomy. And so I mentioned something called gamma ray bursts and GRB afterglows. And for those of you who are scientists or have been in astronomy for a long period of time, you might be thinking, oh, gamma ray bursts, that's a late 90s thing. That's a 1995 thing, that was before I was born. But they have come back into mainstream science again because short gamma ray bursts were now proven to be associated with kilonova, with multi-messenger astronomy, with gravitational waves, this new frontier of science, in 2017. And so for those who don't know, gamma ray bursts are brief, intense flashes of gamma rays and X-rays that occur in distant galaxies. And they have a few different progenitors, but primarily they're neutron star progenitors. And so after the initial burst, a longer lasting afterglow phase emits radiation across the electromagnetic spectrum. And so we have the 2 neutron stars, they merge, releases these intense jets of gamma ray bursts at the point of the collision, at the point of the spin, at the angle of the spin. And these gamma rays, this jet, all right, superheats all the gas, all the matter at these angles. And it leaves like a flame, like a flicker of light. And so the kilonova may only last a few hours to a few days, but the afterglow lasts a lot longer. And so we're able to observe more completely when there's a gamma ray burst afterglow. So gamma ray bursts are something else that Kilonova Catcher observes. So sometimes, because gravitational wave science is still new, we may get a short gamma ray burst detection before we have a verified LVK detection, which and LVK stands for LIGO Virgo Cagra, or the gravitational wave detectors. And so we have to be on top of all of these detections sometimes. And so a few weeks ago, February 6th, we were observing 6 different galaxies looking for this neutron star black hole merger. We were observing 4 different gamma ray burst alerts to see which one was associated with this event. And it was ongoing science. And currently, there are 3 papers being written about the events associated with it. And all of these have the astronomers that contributed from KNC on them. So our amateur astronomers are published. And so they did a little bit of a jump start. So where does Kilonova Catcher come into play? And so we have our primary scientific program, which is what I've been discussing, binary neutron star mergers, the associated optical counterparts. Then we have gamma ray burst follow-up. We have GRB afterglows, and we have supernova. What are the telescopes within Kilonova Catcher? So what do you need to be a part, to be an observer with us? And so we look for a minimum diameter of 20 centimeters or about 8 inches. However, if you have a 6-inch telescope that's able to take images, as long as you are willing to help to learn with us, or if you know how to stack images or do longer exposures, you can reach the same depths, the same magnitudes as GW170817. So we usually are looking between 18 and 22, but when we're looking at the red and the infrared, which is primarily where the evolution of a kilonova is, we look at RFI, and that reaches down to 16. If you can stack your images, which means you take multiple images and push them together, right, we can still use them. You can still participate. And we have resources and members who are currently helping me to write videos and manuals to teach new people how to stack their images, how to pre-process their images, how to apply astrometry and stuff like that, so that their images can be used for science. And so I will rehash this. So how do you receive alerts? So gravitational wave detectors will send out an alert to community. GRAMA, the professional telescope network, will digest these alerts and then trigger KNC. And so we'll say, hey, astronomers, Mark, Michael, hey, can you observe? And we'll send you coordinates. We'll send you a name. We'll send you information about it. And we have a pretty active group of people, and they are wonderful. We don't just send like a blank message. We interact with you guys. We answer your questions. Like, hey, what filter should we be using? When should I transfer over? What can we observe? Where am I observing? Sometimes we'll just send coordinates out because so many things are happening at once. We'll say, hey, you'll be getting a lot of emails. Check the Kilonova Catcher website for all the things you can observe. Check your email. We'll send you a bunch of coordinates. We also have automatic alerts like the ones we get in GRAMA, so that the Kilonova Catcher individual and the GRAMA scientists are getting things at the same time. So not only will they be able to independently observe, but we are also facilitated by scientists. So you're never without the ability to have a question answered. And so you can look at our astronomer guide, which is going to be attached down below at the end of this presentation. But the astronomer guide will walk you through how to submit images and how to get information from Kilonova Catcher website, which will act kind of like Sky Portal, which is what the GRAMA astronomers use. Think of it as like the Facebook for astronomical events. So every event will have its own page for people to be able to follow up and monitor what is going on within the collaborations. And then for anybody's future interest, if they want to watch this video again back, or if they want me to send this to them, it's also part of the QR code at the end. This is kind of the workflow, the information flow. And to kind of just digest this for you guys really quickly is that once you take images, the scientists will synthesize your images, pull magnitude points from it, and they all go, if you look on the bottom right, they all go onto the same photometry plot, the same light evolution, the same figure. And this is what we're shooting for. We're shooting to get, in multiple filters, a full light curve of a detection, of a neutron star merger. And this tells us everything we need to know about what's going on out there, about the science behind it, frontier. All of this is frontier science. It is the next thing you do is the first thing being done. And so how often does this happen? Well, The Global Coordinates Network, which is where we receive a lot of our GRB alerts from, is something that is regularly active within Grandma and Kilonova Catcher. And so anytime you guys provide an image and we're observing something, we release a GCN and it says, hey, we were observing this object. We were observing it for this long. We were able to find this, or we were able to not find this. And so on a NASA database, we have amateur astronomers putting their names down, saying, hey, I did this, I observed this. And this is all recent stuff. And this has not been updated, but we have 3 out this year with Kilonova Catcher on them for the recent GRB, for the recent neutron star black hole merger. What else did we do this year? Well, there was a follow-up campaign of a supernova detection. And so this was a paper I led, and we had Grandma, professional scientists, KNC, and unistellar telescopes all contributing. 337 of these data points, a little bit less than 30%, was amateur astronomers contributing to live science. And this was a really, really cool event too, because there was a whole bunch of unburned carbon in a runaway event. So this white dwarf had exceeded the Chandrasekhar mass after matter accretion, and then it exploded, and there was all this unburned carbon. We're like, why is it there? And so we got to again have frontier science with amateur astronomers, not just formal scientists. And so we released 2 papers on it. There's a paper that describes exactly what's functioning in the environment of the supernova. And we also have one that talks just about what KNC and Grandma did. And so this is a light curve. This is what we want. We want over how many days and all the magnitudes. And you can see all the different KNC instruments, all the different individuals that contributed. If you all are interested, if there are telescope users, there's astronomers here. If you would like to join, I have links for you. You can check out our SciStarter, get some information there. You can join our Slack and ask questions. You can check out the Astronomer's Guide. We also have frequently asked questions where you can see all the theory behind what we do, and also find Grandma's webpage as well. And you can find that here at this QR code. But otherwise, I would like to say thank you for having me present.
Thank you, Christina, or should I say Grandma. Just as a reminder to everyone, this will be posted to our YouTube channel, so you can pause it and copy down the links. I don't think they're clickable on YouTube, but I don't know if maybe, Christina, you can take the links and leave us the last page of your presentation or the whole thing, and people can get the links easier.
Yeah, you can also take pictures now with your phones if you want to. I can put all this in the channel during the question time.
Well, the links on a picture on a phone isn't clickable, and that would mean people trying to transcribe that.
Oh gosh, no, yes. I can send all these lists, all these links.
Thanks. And I'll send them out in an email. Wow. A little bit to digest, folk, huh? Anybody got any questions?
It went very fast. So those links, John, if you send those to me, I can include them with the YouTube.
Oh, cool. Will do. Thank you.
Yeah. So
you can put it in the information section.
That went so fast, Christina.
I'm so sorry. I did not mean to talk that fast. I was trying to mitigate how fast I was talking.
You were faster this time than the first time, and it's still got 25 minutes left.
Oh, I am so sorry. Next time someone's got to wave me down. That's what happened last time. Somebody waved me down and said, "You're talking too fast."
I have a question. Do you have an example of an amateur astronomer's image or data? Or I mean, I don't understand with a small 8-10-inch scope. What am I looking at? A star? Am I doing photometry? Am I taking an image? What am I doing exactly?
So with a 8-inch, with any telescope that you can take pictures with, what you're going to be doing is you're going to take a series of exposures, so a series of images with a certain duration, and then you will take it at a specific set of coordinates that we will provide you. And so what happens is that we're looking for We're going to clear, any light pollution. We're going to clear with our own program. We're going to look for, at specific coordinates, we're going to look for a certain magnitude. If there's nothing there, if it's too bright or if it's too dim and we cannot find within a parameter, like, hey, there's nothing at this magnitude, then that means there was nothing detected. But with your image, what usually happens is that at specific coordinates and a specific image, we're able to filter through any light pollution, any other stars blocking it, and say, hey, there was something at this magnitude. And we're able
What's
to
a
extract
typical
that again?
what's a typical magnitude you're looking at? 12, 15? I mean, is it really low or is it brighter?
It's going to be pretty low, like 18 to 22 on average, but
Oh, geez. I don't think amateur scopes can get that low even. Because I was saying, what about the sea stars? The new sea stars now, they're really good. The smart scopes, I don't think they can go down that low.
No, maybe the 6-inch Raza could, but not a sea star.
we
Yeah.
look anywhere between 12 and 16. So we go as low, as 22.
All right. Well,
But
12 to 16, it can get that, but yeah, 22, forget it.
But remember that that's on the low end. So because gravitational wave detectors are not entirely proficient, and we're not only relying on gravitational wave detection. So when we receive GRB alert, we're going to look over that way, and then GRBs are going to be bright.
So presumably, I mean, you're looking for data points that eventually combined will create a light curve.
Yeah.
Yeah. And so Greg, I think whatever imaging your instrument can provide would plug into the data that that Christina said would be washed according to whatever algorithms they have in order to get the noise out of that, in order to see where your data goes into that light curve.
And so that's why it's a 6-inch, as long as you're able to stack your images, you have longer exposures. The brighter points you can observe with, and then you can also observe until you cannot observe anymore. Well, we have astronomers with 8-inch telescope. We have somebody with a 6-inch telescope, and for the brighter points, they're on it, and then they're like, okay, I'm at my limit. I can't get any more images out. No, perfect, thank you. But sometimes that individual was the only one who could observe because of her location in the world. So she was able to get images when nobody else was.
Right. Essentially, you want the stacked FITS file, not a JPEG, and not individual FITS files. And even I know that the BVRI was one section of filters, but the other was the luminance, something, I forgot what it was, unfiltered. And what was the third one? So it's the stacked FITS, a single FITS, and then that FITS will be combined with other FITS through your scrubbers to produce a light curve that's going to be plotted on that big plot with the big boys scopes.
So
SDSS GRI, 7 sets of filters. Whoa. I don't know what an SDSS GRI is. Can you
MOUSE.
Oh, stop it.
It's non-digital spot, a set of filters that have a specific band pass.
Okay.
Christina?
Yes.
The suggestion, when you're talking about the potential citizen science telescopes that can be used, maybe have a sample image of the potential telescopes. That way people can correlate what they're looking at. I know you've mentioned Unistellar, which is definitely different than the Sea Star and the Dwarf. At least the Dwarf 2, Dwarf 3 I haven't looked at yet. Mine's not coming until March.
Yeah, it's the same size.
But a visual to what you're talking about on the telescopes would probably be helpful.
Yeah. No, thank you. Appreciate that.
And I like that last slide that you had.
Yeah. So there was something I wanted to bring up was that for the stacks and the unstacked, if you have unstacked images, if you cannot stack, we take your images and we'll process them. We'll stack them. You know, if you haven't pre-processed your images, you just take an image and you send it to us, we can pre-process. If you want to learn how to do that, we can teach you. We're actually creating a program now. So the LIGO, Virgo, and Kagra, these interferometers, these gravitational wave detectors, have operating runs. And so the 4th operating run is going on a break on April and May. And so we'll be observing with for gamma ray bursts and other means to detect gravitational waves sources like Kilonova. We're also going to take that time to write a program or finish writing a program that will allow the astronomers to synthesize their own images, to pre-process their own images, to stack them. And that way, everything will be done directly through the Kilonova Catcher website. But right now is that you guys send us your images and we'll process all of them. And then we'll supply you with the magnitude, what we found, how we can help you if you're having issues with your images.
Got a question, Christina.
Yeah.
So the LIGO type interferometers, they've got the 2 legs, right? So does that mean that if a wave front is coming in orthogonal to both legs, it's kind of blind to that event? And is that why you need to build out multiple interferometers like that around the world so you can get every direction, not only get every direction, but be able to pin down the exact direction of the source?
So it's a little bit less precise than that, because if it's not in Earth's, like if it's not in an angle, you know, parallel alongside with the Earth, then we're not going to detect it, or it's not going to be a very strong detection. And so not everything occurs along our plane of existence, unfortunately. And so the reason why we have multiple detectors is, you know, because we are one pinpoint amongst so much space. And so there's so much activity going on the Earth itself that we need to verify that the source of the detection was not anomalous. It wasn't a glitch. It wasn't an earthquake. It wasn't somebody sneezing too hard. So we have multiple detectors across the plane of our planet so that we're able to say, hey, we're getting this in all points evenly. It's evenly distributed. And so the more detectors you have, the more likely it is that your detection is astrophysical. It's not a glitch.
Do you need multiple interferometers to pin down? Oh, let me phrase it a different way. If you just have one, can you tell where the source is in the sky, or can you only pin it down to like a plane, if that?
So we do not have interferometers strong enough to pinpoint anything, no matter how many we have. However, with more detectors, we're able to close in the space that it could possibly be much better.
Okay. Thank you.
So I understood the 8-inch or 20 centimeter SCT type of telescope and above. For the 6-inch refractor, are you strictly APO or achromat also?
Say that again.
And for your 6-inch refractor, let's say, is the precision of color color correction required, or is just a simple achromat work where wavelength of color doesn't matter? Say you've got a luminance filter on there or a BVRI set, color correction isn't going to be done properly in an achromat.
No, but I do believe that we have tools to adjust for that. However, that's a good question to ask, for me to ask one of the amateur astronomers who does do this.
Okay.
So we're writing it. So send me that question and I can get back to you on that.
Will do. The simple part of the question is APO versus achromat.
Yep.
And why?
We were discussing that at the last meeting. Forgot the answer. I think it's undiscussed right now.
Thank you.
Yeah.
So I mean, along those lines, I mean, aren't we most interested in the luminosity, the apparent luminosity that we're detecting, right? Or is there a spectrum analysis is being performed as well? I mean, I think that's where the difference between an apo and an achromat would come in, is when you're talking about spectra rather than luminosity, right?
So there's no mechanism for spectroscopy now within Kilonova Catcher, but Grandma does its own spectroscopy.
Interesting.
We're just looking for magnitudes. We're just looking for photometry.
Okay, so in photometry, we're looking at apparent luminosity and the measures there in order to fit the light curve, right?
Yes.
You're referring to the spectroscopy, sorry, my Brooklyn, made by an amateur viewer?
Yes, it's part of the achromat versus APO question, Jim.
Okay,
Because if spectroscopy matters, then an achromat is out. But since it doesn't, and it's just luminance,
Right.
an achromat could be in.
You know, you are the third person to ask about the APO and achromat, and so spectroscopy. And there's no system for it yet, but the spectrometer that we use, the location, the observatory that we use, I don't see why they could not process that, which we don't have the program to process spectroscopy, is what we're saying with your images.
Yeah,
if
I may be speaking out of turn, or it's a long shot, but if there's no one that could identify that, I have a member of our club that I mentioned to you earlier in the day. He actually made that for his research on the eclipse. And he 3D printed it and used it on his telescope. So if I can get him to talk during a Zoom session with you, if you want, if you don't have the resource, I'll try reaching out to him.
I'm sorry, Jim, made what? I'm lost you there.
He made his own spectroscopy device.
Oh, okay. That's
using computer programs that he had.
Yeah, I understand.
Yeah, he was doing all the work, and I was sitting there with my eyes rolling in the back of my head and drooling as he was doing it because I didn't understand anything he had going on.
Yeah, the CWG 700.
It's not the tools that we don't have, like the physical tools. Like I'm sure that there are astronomers within Kilonova Catcher who also have the ability to do spectroscopy. However, there's no basically with spectroscopy, you have to have enough data for it to create a complete spectra.
Right.
And so a handful of amateur astronomers isn't going to able to do like enough spectra. And so we do spectroscopy with an observatory on the grandma side, but rarely, because GRBs are not gonna, we're not really gonna do spectra with that. We did spectra with the supernova, but that was like long arching, and there hasn't been enough neutron star black hole or binary neutron star detections to do spectroscopy for. So it hasn't been a priority to create a program that'll be able to synthesize spectra or spectral images.
Recapitulate, luminance is what's important, not spectrum.
Yeah. So it's something under discussion, but right now there isn't. The gravitational wave detectors are either not detecting correctly enough binary neutron star or neutron star candidate gravitational wave events, or there aren't enough occurring in the universe. So I do research with the Vera Rubin Observatory, the largest ground telescope in the world, set to green light in May. And optimistically, it's 14 with the most stringent criteria. So that means that we're looking specifically for Kilonova. It's going to rise really fast in the U in blue, and it's going to fade really fast in towards the red and the infrared. And so that's what the metric is saying, like, hey, this is evolving and it's looking for this criteria. And so it's looking for a kilonova. Optimistically, it was 14 events over 10 years. That's roughly 1.25. All right, over 10 years, the length of the survey that Vera Rubin is doing. Pessimistically, it was less than 1. And then the median was 6. And so that 6 number, that median number actually makes sense because there have been 5 total events since the end of the last operating run that had a neutron star involved in it. And so recently, within the last 3 months, LIGO, Virgo, and Kagra have been detecting a lot more gravitational waves with confidence, with a higher confidence. So with a better FAR rate, right? And that's great because that means we're getting more detection, more ability to observe. We're classifying more things as having light involved. But we are not sure over time so we're sure over time that we will improve our detectors, but we cannot control how many neutron stars are actually out there. We do not have a population for them because we only have one, really confident observation. And then we have a few, 5 to 6 not so confident observations with neutron stars involved. And that's why we look for gamma ray bursts. And so we do a lot of science on short gamma ray bursts. We do a lot of science on supernova, neutrino detection as well.
So with those other modalities, the neutrino detection, do you get directionality out of the neutrino detection? And there's multiple sites that are doing neutrino detection. So presumably, if there's a neutrino burst, these multiple sites will spark at the same time.
Yep.
And neutrinos, because of the kind of particle they are, they're probably not going to be influenced by gravitational wells the same way that light or gravitational waves are going to be, correct?
Yes.
And so that'll be your first indication that you've got a kilonova event.
Yes, exactly. So we do respond to neutrino detections with like IceCube, and we follow up on them as well. We do optical observation with them.
Okay. Okay, so then the gamma ray bursts, do you get directionality out of those?
It's a little bit more like of an estimate. So we'll usually look at things within a few arc seconds, and we have to find the gamma ray burst. But what usually happens is that SWIFT, which is a satellite, will detect it first.
Sure. And
then we'll follow up on it to look for the upper limits of that event. We do so quickly. Sometimes because it doesn't like it doesn't have the best confidence. We don't find an upper limit. We don't find the gamma ray burst. We don't find where it actually was. But most of the time, we're pretty confident with gamma ray bursts that we know where they are and we're able to observe them. That's why we actually have three papers currently on 3 different gamma ray burst detections that happened this year.
So you'll basically send out an alert that'll give an RA deck pinpoint or approximation rather than just say, go west, young man. Just see what you get.
We never tell them go west. It's always a specific set of coordinates.
Yeah, I think that's what some of the questions we're leading to.
Yes, it's always a specific set of coordinates. So we always have a heading, there's always a direction for it. But whether it's exactly at that point, yes. But we're never going to tell the KNC astronomers to use their resources if we're not, within 80 to 90% have a confidence rate that it's going to be in this location.
First start to the left and sail on till dawn.
Yeah.
I like it.
That was another part of the sensors out there. I mean, the best sensors to be able to look at these events are going to be our space telescopes and the various sensors that are on board those things. But because they're scheduled out for years ahead, the challenge would be being able to tap into them on cue, right?
Yeah. So phenomenal statement. You're the first individual that kind of called it out. Hey, why aren't you using these big telescopes and why we're not? It's because these alerts are triggered. It's not like something static. These large telescopes don't want to reserve time for it because that means they have to stop whatever survey they're doing. We have tried to get time on JWST. It's looking much more hopeful with the Nancy Grace Roman telescope. I actually met with Dr. McQuinn, the mission head for Nancy Grace Roman telescope, last Friday to discuss exactly this. And because obviously all the work I do with Grandma, she was very interested in hearing about time domain astronomy. And hopefully because the Nancy Grace, because the Roman telescope is going to have such a large field of view, at all times, if we're not sure where an event is, it can say, hey, we're looking for this, and it'll take a picture. And all those pictures can then be processed by scientists, which is going to be great for time domain astronomy, for multi-messenger astronomy. Mm-hmm. But for the Rubin telescope, I just published two papers on this, that there is no, time of opportunity plan for Rubin, really. And so it's just hoping that as the data comes in, that we'll be able to say, hey, there was an alert at this time, LIGO, Virgo, and Cobra detected it. Could we get the images from Rubin within this parameter? And we're going to hope that Rubin was looking at the right place, at the right depth, at the right time, to see if we can get, full photometry. And that's why Kilonova Catcher is so important to multi-messenger astronomy, because the more telescopes we have to observe, the more likely it is, even the ones at 6 inches, that we can get full photometry. So every data point matters.
Yeah.
I have maybe a more basic question. I think a nova, supernova, now it's kilonova. So this neutron star merger, how does that stack up, say, energy released in comparison to maybe some standard supernova type event? And is it maybe close, but a lot more is in gravitational waves versus electromagnetic spectrum?
Supernova is much wider because there's a lot more matter going through much more different processes. There's a lot of greater variety, greater diversity of matter too in supernova events. But binary neutron star mergers are going to be more powerful in the sense they'll produce higher gravitational waves because of how dense and how compact everything is happening. So all this matter is trying to be at one spot at once, and then they merge. So already you got two planets beefing, all right, internally. There's internal issues going on, and then suddenly they're fighting. And so now there's all this like tension here in one spot. It causes this jump, and that's what gravitational waves are. It's why supernova don't, while brighter, don't necessarily produce gravitational waves as strong, because the matter isn't as dense. It's not all trying to be in one spot.
Okay. So the merging neutron stars put more of, whatever energy is coming out of it into the gravitational energy pot versus electromagnetic, for instance.
Yeah.
Because of the.
Yeah, that's exactly it.
Excellent question.
Yeah. See if I can find it.
Supercalifragilisticexpialidocious.
Right. One of the individuals that I was presenting to sent a warning, please no acronyms. And I'm like, you know how many words have to come out of my mouth? So I try to remind everybody as I go through. So they kind of see it a little bit here, like binary neutron star have weaker amplitude due to a lower total mass, even though they're higher frequency. Binary black hole mergers will have a stronger amplitude because there's more mass there. But the interactions of the matter is less. The diversity of matter is less in black holes than there is in neutron stars. We do sometimes, I didn't get time to, or I didn't find an appropriate place to say this, but binary black hole mergers will sometimes have optical counterparts because of accretion disks. So that's also really cool. We do follow.
Say what, please?
Say that again?
Because they do what, please?
They have accretion disks. So the
Okay. I
black hole
missed
will have
that.
accretion disks. That matter will all get fired up, and sometimes it'll create gamma ray bursts and ejecta.
Yep. I just
So
missed the word that you said, but I
yeah,
was focusing on the 10 to 100 hertz versus a few kilohertz. 10 to 100 hertz is something that vibrates in your chest.
yeah.
I mean, you feel the ground shake with
Yeah.
that frequency.
Hmm. Yeah, very interesting stuff. Thank you.
Well,
Yeah.
great question too, Jeff. Thank you.
Thanks.
Wow.
Any more questions?
Right on time, Christina. Thank you.
I just had one
Yeah.
Okay.
whenever we're using our telescopes to gather information, is there like a particular type of camera that we have to attach to our telescopes, or like in order to gather the information, or is there um a a a, a guide that we can use?
That's a good question. We don't have a guide currently for like specific cameras or setups, but that is something to be considered because of the technical involvement of the
Yeah,
camera.
what's the length, the duration of the exposures recommended? That may answer that somewhat.
I do have a slide for this one moment.
Are we talking 30-second or 5 minutes?
So we do three, sometimes we'll ask you for 60 seconds. So 5, 10 minutes. Sometimes we'll ask you for much longer. Sometimes we'll do, I think a standard is like 10 exposures over like 300 seconds each.
Oh, I see. Exposures 30 minutes to 2 hour sensitivity. That is the range of a cooled CCD or CMOS camera, Lucas,
Right. Your typical astrophotography setup.
for deep space, not for planetary. It has to
Yeah.
be a cooled detector.
Okay, okay, thank you. So um and so just so like not like a like it'd be like a video that we're taking, but just like but several images rapidly over a given period of time.
Yes, Colin, you got it.
Yep.
Okay,
A
all right,
video
thank you.
with a 2 hour exposure per.
Yeah, so you're not
image.
closing that shutter. You're not closing that shutter for several minutes.
So you can have a DSLR camera with the proper cooling attachment
Mhm.
that kind of like looks at like a big box in front of the camera,
I would
or
say that's
your
a
typical
waste of.
ZWO, canister camera.
I would go ZWO, then waste your time and money on a DSLR that's going to get very hot.
Right. I only mention it because we've got a member who actually has one of those.
Yeah. 2 hour exposure with one of those would cook your sensor.
All right, okay, thank you. And then and then we could just uh um and then if there's like a and I guess like if we're able to convert these are the images gathered from the cameras attached to the telescopes to to our computers to send to Kilonova Catcher.
Yeah, so then you would just
Yes.
use the if you have an SD card, you can transfer it that way, or if it's automatically connected to your computer, even better. As soon as you get those images, you send them our way.
Okay,
And
all right, thank you.
you could stack them the way you'd normally stack any image and then just send the final fits. And if you don't know how to use a stacker program, then you could just set up all the individual frames as she suggested earlier. Some
Yeah.
of that
All right.
stuff will be in the links that you're going to send me, right? Some
Yes.
information.
Although the
Is the
pre-processing,
handbook is the handbook available for people that haven't signed up yet?
yeah,
Okay,
the
that might
astronomer's
be
guide, everything's on the website.
good for people to actually understand what they're up against.
Yeah. Yeah.
I think you got some eager beavers here, or headbanging against their computer. I'm not sure which, but
Yeah, if only we didn't live in Connecticut.
Yeah.
So like renting time on some of those scopes that are down in Arizona or even South America, Chile, would be seems like more productive for us.
There's a running joke within Kilonova Catcher's Slack that they'll ask the scientist who's talking to them, could you stop the rain for us so we can take images?
Yeah.
And you always have to answer, yes, I'll see what I can do. Always.
You got to get your members to stop buying something new before you're ready to do it.
Yeah.
Good
Although
point.
I'm a little bit more facetious. Every time they ask, I'll come back like 5 minutes later with a different god saying no.
The killer cloud catcher.
Yeah.
Christina, I'd like to thank you on behalf of the ASGH. We all thank you for spending the time to share this with us. And really, it was as fast as it was, the questions made it all worthwhile. It was worth it, the Q&A session.
I'm so glad that you guys liked it. Sorry for talking so fast. Something I need to work on. I'm aware of it. But thank you so much for your wonderful questions, your insights, your advice, and your expertise. You are an incredible group of people, and I really appreciate talking with you guys.
Thank you for
Thank you.
joining us.
Yeah, bye.